Last time on Saturday, and for people who came in yesterday, we talked about friction. And when we talked about friction, we talked about what is the origin of friction force. And we also talked about if you have if the surface area between the two objects is large, you increase the frictional force. And this is a good example for the relation between the frictional force and surface area. What you see here is two old catalogs that we had in physics department, and they were going to throw them away. And what we did is we took them and we put them that way. Alternative page, the same as you see it. Okay? So no glue between them. Okay? And so we did that. Someone has spent time doing this. And hopefully his work is not going to be wasted. So what I'm going to do is, do we have any bodybuilders in here? Ali? Ali? What's your name? Ahmed? Ahmed? So we choose two big guys in class, and I'm going to ask them to pull on each hand without shaking it. Do not shake it. Okay. The point is not to shake it, and pull on them, and if they are strong enough, they will pull them apart. Okay, guys? Wait. Okay, guys, pull. Do not shake it. Pull. More. See how large is the friction force? It's incredible. You cannot believe it. Can we do this? All what we have done is the following. We got 2 pages. May I? Can you pass 2 pages? Are you sure? 2 pages. See? Can I move this? Of course I can. The friction force is very small because the surface area is just that area. That page is the area of that page. What we have done here, we have multiplied the surface area by using so many pages between those two catalogs, and that's why Ali and Ahmed were not able actually to take them apart because the friction force is huge between them, and it's only surface area. Every single page, yes, and that's huge surface area. Okay. The friction force increased on that because we have increased the surface area. It's not only the area of 2 pages, it's the area of 500 pages. Okay, so this is how huge the surface area can be. Excuse me? One more time? 2,000. Okay. Does anyone want to try it one more? Sharif.
That means that the formula that we have for the friction force
the formula is correct, but it's the normal force from that page on that page times the coefficient of friction multiplied by 500 of 1,000. That's why I was able to move this.
Oh, yeah.
Because the friction force now between those two surfaces, the friction force between those two surfaces equals to the coefficient of friction times the normal force. And the normal force in that case, it's just m times g. And that's a very small m, small g, and it's the surface area. And here it's multiple of those. So we have increased the surface area, we have increased the friction force. And that's a good example for the use of friction force. And we have also talked about some other examples during the last class. In here, I'm going to talk about friction force. If we assume that we have an object that has a mass m, and if we need to find the if we push it by a force F, and if we need to find the acceleration, if we have friction, if that surface has some friction, So what we do is we first draw the free body diagram, and if you look at the free body diagram for this, that's really easy, really simple. It's the friction force along the positive x-axis. Sorry, guys. The force F, the force that we push the book with, or the object with, along the x-axis. The frictional force along the negative x-axis, because it's always in the opposite direction to the motion. The mg down and the normal force up. This is all the forces acting on that object. So if we look at the x-axis, we have a positive F minus the frictional force equals to mass times acceleration. And if we look at along the y-axis, we'll find that the normal force minus mg equals to 0 because there is no motion along the y-axis. And from that we can get to know that the normal force in that case equals to mg. And if we know the normal force, then we can calculate the frictional force, because simply the frictional force equal to coefficient of friction times the normal force. Since we have a motion in that case, the coefficient of friction is going to be the kinetic coefficient of friction, because that's constant. That depends on the nature of the two surfaces, and it's tabulated. Either we measure it in the lab or we find it in a table of constants. Then the frictional force minus mu k times n equal to mass times acceleration. We know what's n, that's mg. We know the force F. Then we can find the acceleration from that simple equation. Everything we know F, we know the coefficient of friction, we know the mass of the object, we know the gravity, then we can calculate the acceleration in that case. So that's a good exercise for the motion of an object that on a surface that has some friction. Farida first.
I don't understand, isn't n on the y-axis, why are we putting F minus n mu times n?
Oh, that's good. Yeah. This I should have written this from the beginning to be the frictional force. It's F minus the frictional force.
Yeah, where did you get n from?
But we know that the frictional force equals to, so I should have written that F equal to, so minus frictional force, it's actually kinetic friction, equal to mass times acceleration. But we know that the frictional force equal to mu k times n. So I replace that by mu n. Azam?
How to calculate that?
F, that's given.
The problem in the homework.
You talk about the assignment, right? You can read the problem, then I will answer that for you. Do we have motion? Do you have acceleration in the problem in the assignment? I can discuss that, guys, with you after class. Okay, I can discuss it with you after class. But anyway, Sharif.
Doctor, later on you said that if an object is hanging by a rope with a tension, the more the angle, the less the angle between the tension force and the object, the bigger the
That problem? Yes. The bigger the angle, this is as big as it can.
Yes, the 90, and the smaller the angle, the higher the tension.
The smaller the angle, the higher the tension in here. Yes. Yes. In that case, yes. Because the tension T1 and T1 in that case, if I remember correctly, T1 will equal to, I think it was equal to mg over 2 sine theta, something like that. And if theta equal to 0, then the tension is infinity. Okay, now taking that into another extra dimension, a little bit harder problem, we have a mass m1. A mass m1. That's 1.5 kilogram. We pull it in by a horizontal string. That's a string that has a tension equal to 90 newtons. It slides with friction where mu k equal to 0.51. That's what's the units of mu k? It has no units. On the top of second object that has a mass m2, that m2 equal to 3 kilogram, which in turn slides on a frictionless floor. This floor has no friction. T is bigger than the force of friction. T is more than the force of friction. What is the acceleration? Acceleration of the second box. Of M2. What is the acceleration of M2? Then I have given you 3 answers and one of them is correct. So what to do? Yeah, that's good. We start by drawing the free body diagram. Which one? For which object? For M2? For M2? For the whole system? For M1 and M2? No, for M1 alone and M2. For M1, what are the forces acting on M1? Normal force. Normal force. And 1 gravitational force. M1G. And tension. And friction. What is the direction of the friction? Color. Frictional force. Is that kinetic frictional force or is that static? It's kinetic frictional force. Okay, this is the free body diagram for object number 1. Object number 2. M2. So we'll have normal force from the floor on M2. And I'm going to call it N2. And
was the M1
and the normal force down in here. M1 is pushing on M2, N1. And friction force in what direction? Oh, no, that's good, that's good. Men is saying it's in the opposite direction. The friction force in that case?
There's no friction.
How do you know? There's no friction in here, but there's friction in here.
مش أول أنتوا أصلاً ميوكي فوق.
See, mu k is the coefficient of friction for the two surfaces. Not for an object, it's for the it's the characterization of the surfaces. Okay, Shinawi. Okay? Okay? Okay. Any other forces? Any other forces? MG, M2G. Guys, let's focus on what we're solving.
I want to say that there is C because the reason that every action and the reaction.
There is what?
The problem when we said every action and reaction to us.
That's Newton's third law.
Yeah, but we were close to each other and we said that.
Yeah. That's why this is in here and this in there.
And the C we don't do a lot of C.
What C?
C.
T? No. Tension, you're pulling that force with that force. In that case, there will be a force on your hand from that object. But we're not including that force on your hand. So we're not considering your hand that's pulling that M1. No, it's not going to affect it. Ali.
What is the N1?
N1? Well, Object, what's the N1? What's the N1?
Why is not M1G?
What's the N1? What's the N1? Because I don't know if it's the M1G or not.
How do I do it?
What's the N1, guys?
The normal force acting force.
The normal force from that surface, from the red object on the brownish one. This is the normal force. And there is also normal force from M1 on M2. Those two forces are equal in magnitude and opposite in direction.
So that means that those N1 and N2 cancel out?
Excuse me?
Those N1 and N2 cancel out?
N1 does not equal to N2. Again, if you look at object number 1, what are the forces that's acting on object number 1? You have mg down, m1g down, then m2 is pushing m1 up. I call that N1. Then forget the friction forces for now. I'm not going to talk about the x-axis. What are the forces along the y-axis on object number 2? The object number 2, M1 is pushing down on object number 2 with a force equal to N1.
Now, this is my question. Why is not mg? But if the N1 is more than mg, then it's the same.
Because N1 is not mg. Does not equal to mg. And N1. Sorry. Yeah, it's mg. But I'd rather can write it N1 for now. Yeah, we'll find out. From here it's going to be mg. But the normal force is not always mg. But in that case, it's mg. That's why I would like to put a general n, then find the value of that n later on. Okay, good.
It's not always...
No, because if you are in the elevator, and that's the example that we have talked about before, normal force does not equal to mg, right? Okay, so this is the free body diagram. Remember, we need to find the acceleration of that object of M2. So I'm going to concentrate on M2 since he's asking us about the acceleration along the M2 for M2. So I would say along the x-axis, sum of the forces equal to mass times acceleration. What are the forces along the x-axis? That's object number 2. Frictional force, it's only frictional force equal to MA. Isra is saying, well, it has to be negative because it's pointing along the negative x-axis. Okay, good. Now, what is... Can we calculate the acceleration from that equation? Can we calculate the acceleration? Guys, can you see? Can we calculate the acceleration in that case? Yes, if we know what is the frictional force. Do we know the frictional force? So, from that equation, no, we cannot. We have to find what is the frictional force. We know that if you take here that for example, sum of the forces along the x-axis will equal to mass times acceleration. Mass times acceleration. If you write that equation, you will get T minus frictional force equal mass times acceleration for object number 1.
Only number 1.
Oh, yeah.
No friction, right?
Okay? Right? Oh, but okay, but I changed that now. If I change, I can choose the coordinate system the way I want, and the result is going to be the same. Okay, so I choose that in my solution on the whiteboard. I choose the x-axis to be different. That's okay. So if you look at this equation, we still cannot get what is the friction force. But if we look at along the y-axis, we know that the friction force equal to mu k times n. Which n? Yeah, n1. And Ali kept saying that actually the n1 from this coordinate system, if you apply Newton's second law along the y-axis, you get n1 equal to m1g. So friction force will equal to mu k times m1g. If we apply Newton's second law along the y-axis, you get n1 minus m1g equals to 0 because there is no motion along the y-axis. Then you can get that n1 equals to m1g, and that's what I did. Now we know what is the friction force. If we put that information here, then we calculate the acceleration. So it's going to be uk times m1g divided by n2. And if you plug in the values, you get the answer. And the answer is going to be again, it's the same answer as I got. Here's the acceleration equal to m1 times mu kg divided by m2. Right, guys? Same answer as you see on the whiteboard. And if you put in the numbers for numerical values for m1, m2, mu k, and g, you get the answer, and the answer is going to be 2.5 meter per second. Then someone will say, what about the negative sign? Here I have a negative sign, while in here I do not have a negative sign. It's direction. Sharif.
Doctor, how can we separate the acceleration of M2 by the mass of S2 by itself if both are on top of each other?
How can we separate the acceleration of M2?
Like the M2 that in the formula that we use.
That one?
Yeah. M2, as long as the other box is on top of it, is the mass of both. Isn't it?
No. When you draw the free body diagram, you separate the two objects from each other, and you treat each object as if it's one object, and you concentrate on the forces acting on that object. And if you do this, then you get all the forces acting on that object. So if you're talking about, what Sharif is saying is M1 affects M2. M1, the one on the top, it has some effect on M2, and that's true. Here it is. It's here in N1. So I did not ignore that effect. It's there.
But it's more than this. It's M2 and M1. Two masses.
Yeah, what I mean is that the normal force from the ground to M2 is going to include mg and n1.
The normal force
From the ground to M2,
N2.
Yes, it's going to include the mg and the normal force of...
No. The N2, if you need to find the value of N2, now Sharif is asking us, can we find the value for N2? What's N2? Okay, if some of the forces along the y-axis equal to mass times acceleration, that means that N2 minus N1 equals to negative M2G. That N2 equals to negative M2G, negative plus M1G. So what you're saying is M2 is affected by M1. Here it is.
But isn't the sum of all forces in the y direction equal to 0? Because there's no acceleration up.
I mean, there's something wrong.
Yeah.
Oh. I know.
Here it is. Right. You're right. So M2 is the normal force from the floor on M2, but the magnitude, it takes into consideration what's on the top of M2. We did not ignore it. It's there.
So M2 is equal to 1 plus M2 on the opposite direction, negative M1 plus
Yeah. Yes. Yes. It's equal to N1 plus the mass of M2 plus G. N1 plus.
I don't know why we didn't take that into consideration when we're calculating the acceleration. Because they are on top of each other.
Yeah. In here,
Yeah.
because we talk about the force along the x-axis, and the ends, N1 and N2, those are forces along the x-axis, y-axis. Okay? Amira.
If you increase the tension on the upper mass, the acceleration will still be the same.
Say that again.
If you increase the tension on the on M1, the acceleration of M2 will still be the same.
That's a very good question. Okay, let me look at it. We increase the tension on M1. Well, A2 be the same. If I increase the tension in here, then I'm changing,
Changing MA1.
then actually I'm not doing anything. It's not going to do anything.
You're changing the tension, you're increasing the power. I'm talking about that you're going to a
What power? What power?
يعني
What is the power? What is the meaning of power?
increase tension.
If you increase the tension, you increase the force that you pull M1 with. Okay? Then, let's look at the equations. Just look. If you increase the tension in here, all what you're going to do is you increase A1. You're going to increase A1, but you're not going to affect A2 at all. You're not, if you affect the frictional force, then you might affect A2. If you increase the tension, you will not change the frictional force because the frictional force depends on UK and M1G.
It doesn't make sense when I put
No, it's
Depends on the view. How to get to if it's already moving, خلاص, what she's saying, it won't affect it. But if it's not moving yet, it will.
that's a different story.
Yes, it is.
That's a totally different story. If you're changing it from static to kinetic, now we are at steady state. Steady state means that you're pulling it with the same acceleration, you're moving that with the same acceleration, and M2 is going to be doing the same. And if you move it with the larger acceleration, nothing is going to happen to A2. Nothing is going to happen. It's going to stay the same. It will not affect it. It will affect the acceleration of A1, and no, A1 is not equal to A2.
No, I'm not saying they're equal. I'm saying that A1 affects this friction, so it's
How so? How so? If you increase the tension,
And if you increase
if you increase the tension, will the frictional force get affected?
so if you increase the tension, the force will fall off.
What?
The M1
Guys, concentrate on what I'm saying. Marim, what's your name? This is physics? Are you solving the assignment? Okay, this is tension. If we increase the tension, that's what Samira is asking. My question is, Amira is saying, if we increase the tension, will A2 increase or will it decrease? Then if we look at the equations, if you increase the tension, will the frictional force change? This is the most important part in here, because actually the acceleration of A2 is only affected by the frictional force.
Okay.
So what happens when you increase the tension?
Mean, right? This is the frictional force. So A2 is only affected by frictional force. So if we increase the tension in here, keeping the same acceleration, it cannot happen. It cannot, yeah, you have to increase the mass, and that cannot happen. So if you increase the tension, the acceleration will change, but the frictional force is going to stay the same. It will not change. The frictional force, that depends on the normal force. It does not depend on the how fast you move, what is the acceleration you move the object with. So if I move that object in here, that way or that way, slower, with a small acceleration or with high acceleration, the friction force will not change. The friction force is only function of the normal force. The frictional force equals to the UK times the normal force. So it will not, acceleration will not affect it. Amira? That's a very good question. Sure.
When we did the mobile thing, when we did this, so I don't understand why when we
Oh, this was Newton's first law. Yeah, laws of inertia. That was Newton's first law. I had to move it fast in such a way that the force I pull it with is more than the friction force to ignore the friction force. So if there is no friction, Ali, if there is no friction, and if I pull this, it will stay the same. If there is no friction between the mobile phone and the paper, and the paper and the table, if there is no friction, if I move this will stay the same. Nothing is going to happen. It will not move. But in order to do the demonstration in front of you and make it effective, I have to move it in such a way I should minimize the frictional force. And in order to do so, or actually I should move it with a force more than, much more than the friction force. That's why I do it that way. Very fast. Then what I'm doing is I'm moving it with a force, much more the frictional force, so it's exactly as if I'm ignoring the frictional force.
But we just said that the tension of the force has nothing to do with the friction.
I'm moving it with a force much more than this. So if you look at that equation, this is 3 million and this is 1. So that means that tension equals mass times acceleration. Okay? Good. Good. What else? We started with a simple problem. That's a surface, a horizontal surface with some friction. Now we're going to have an inclined surface that has some friction. And we will need to find out, in that case, what will be the acceleration, I guess. Yeah, we need to find the acceleration. So in that case, in order to find the acceleration, we have to draw a free body diagram. We have to choose our coordinate system in such a way it has the x-axis will be along the direction of the motion. We have to keep in mind that we have now a frictional force between that object and the tilted surface. So if you look at the free body diagram, this is a complete free body diagram. We have mg pointing down. We have normal force perpendicular to the surface. And if I draw it, guys, if I draw it that way, or if I draw it that way, it doesn't matter, it's the same thing. And we have frictional force, mu k times n, that's opposite to the direction of the motion. If you look at those forces, all of them are either along the x-axis or the y-axis except mg. So I have to resolve mg into two components. One that's along the x-axis, that's going to be mg sine theta, and one that's along the y-axis, that's going to be mg cosine theta. And if we do this, No. This is going to take mg cosine theta, y-axis, and x-axis is mg sine theta. And if we, yes, and if we apply Newton's, Farida, if we apply Newton's second law along the x-axis, this is what I'm going to do, and equate that to mass times acceleration, and apply Newton's second law along the y-axis, and equate that to 0, that's what you get. mg sine theta, that's positive mg sine theta, that's the 1, that's positive, minus frictional force, negative, equals to mass times acceleration. Along the y-axis, normal force, positive, minus mg cosine theta equal to 0, and from that we can say that the n equal to mg cosine theta. If we know n, if we know the normal force, we can simply calculate the frictional force. Normal force equal to mg cosine theta, and accordingly the frictional force equal to mu k times mg cosine theta. This is the frictional force. Now, if you look at that equation, we have mg sine theta minus mu k mg cosine theta equal to mass times acceleration, and from that equation we can say that A equal to sine theta minus mu k cosine theta times g, or we can say that A or g equal to sine theta minus mu k cosine theta. So we can get A in that equation. Let me finish. Azan, you want to ask something? Okay. Static friction. Now I'll take you one step backward again. We talked last time about static and kinetic friction, and we explained the origin of static and kinetic friction. And we have stated that the coefficient of friction, the static coefficient of friction, is larger than the kinetic coefficient of friction. It's always larger than the kinetic coefficient of friction. And if we need to calculate the static coefficient of friction between any two surfaces, so if I give you two surfaces and the chair, if I give you those two surfaces, the chair and my mobile, and I ask you guys to calculate, actually to do an experiment, to calculate the coefficient of friction. What are we going to do? What I'm going to do is, in the simple experiment is, I'm going to put the object, and I will start tilting that object a little bit, until the point that that object, the mobile, is about to move. It's not moving, but it's about to move. It's about to move. Then I will measure that angle, theta, then we'll go to the board. So go to the board and see what happens then.
There's another reason why instead of something secure, you can measure the force that makes it move.
How can you measure the force?
So it's some ruler that holds it and force is measured.
How can you measure the force?
Well, there's you device to look at.
And if you don't have the device, what to do? Then you need a force sensor to measure the force. And if we don't have the force sensor, and we still need to measure the coefficient of friction, we can still do this. So this is what I did. That angle is theta, and that object is about to move. Okay? In that case, I will draw the free body diagram. That's mg. That's the frictional force upward. And that is the normal force. And if we write Newton's second law, then I have to resolve that m2g into two components. That's m2g cosine theta, and that's m2g sine theta, and that angle is theta. So along the x-axis, sum of the forces will equal mass times the acceleration. What are the forces in that case?
Why are we writing to mg sine theta?
It's mg sine theta, What is the 2? What's 2? Sorry. mg sin theta minus frictional force equals to 0. It's about to move, it's not moving. And from that case, mg sin theta minus mu k, mu n, yes, n equal to 0. Then we need to know n. N will equal to mg. And taking that back, this is J, this is the Newton's second law along the y-axis. Then mg sine theta, mg sine theta minus mu times mg cosine theta equal to 0. Yes, I'm sorry, mg, it's n equal to mg cosine theta, n equal to mg cosine theta, you're right. Then if we do this, then we can say that mg sine theta equals to mu times mg cosine theta. Mu will equal to mg sine theta divided by mg cosine theta. Yeah, I'm thinking. Then you end up having mu equal to tan theta. So if I measure the angle, if I just measure the angle, I can get the coefficient of friction. And that's a simple experiment to calculate the coefficient of friction between eight surfaces. Yeah, if you know theta, tan of that angle theta equals to the coefficient of friction, static coefficient of friction. Okay, guys? Then?
It doesn't depend on the material itself.
Of course, mu is going to be different from one material to another. Mu, the angle is going to be different. If I put this, or I put my mobile, the angle is going to be different. And if the angle is different, then mu is going to be different. Good question. What else? Nice. I like the class today. We have so many good questions today. This is good. Okay, so you all get bonus.
5%?
You're 100%. You all get a bonus of 100%. Now, Yasmin, you're going to solve that for us. You have an object that has a mass m. That mass is 10.21 kilogram, and it's at rest. The coefficient of static friction between the floor and the object is us. That's 0.4 newtons. Thank you. So I have only two people in class who knows that what they are doing. Friction force does not have units. So if I say Newton, then that's something wrong. Us equal to 0.4 and it's unitless. A rope is attached to the box and pulled at an angle theta equal to 30 degrees. So that angle is 30 degrees above the horizontal with the tension equal T equal to 40. So we know the tension. Does the box move? Yes? No? Actually, we cannot tell. Yasmin, so what do you think? I'm going to pull it with a tension equal to 40 newtons, and I'm asking you, would you be able to move that object if you pull it with a tension equal to 40 newtons with an angle equal to 30 degrees with the horizontal? We have to draw the free body diagram. So I will draw that even if you were just saying it to buy time. I will draw it. So here is your free body diagram. And forces. What are the forces acting in the object? mg down. Perfect. And upward. Perfect. And friction is along that direction. and the tension will have two components, T cosine theta and T sine theta. Perfect. Will it move?
You have to calculate the force.
Yeah, we have to calculate the net force along the x-axis. So I'm going to say sum of the forces along the x-axis will equal to mass times acceleration. If the acceleration has a value, then it moves. If it does not have a value, then it will not move. So what are the forces along the x-axis? So T cosine theta minus the frictional force equal to, if it's more than 0, if this is more than 0, then it will move. If it's less than 0, then it will not move. So let's find out. Equal to mass times acceleration. Now, T cosine theta, that's T, that's 40 cosine 30 minus mu times n.
Isn't the mu here, don't we find the mu, if you use this mu s?
Then if we know the I of S, we can use mu s, because if the force that you're providing is more than the static coefficient, the static frictional force, then it will definitely move. And because we know that the static frictional force is more than the kinetic frictional force. Okay, then that's correct. Then equals to, we need to find that this equals to what? So we need to find n. Ali is saying we have to find n. If we look at this along the y-axis, n plus t sine theta equals to mg minus mg equals to 0, which is exactly as perfect. That's okay. Which means that n equal to mg minus t sine theta. Does anyone have a calculator? Sharif? N equals to n 80? Kilograms. Ali. Newtons. It's a force. So now we know n. So this is 80.16 times 0.4, times 0.4. And this quantity, 40 cosine 30, that's 40 point something. It's obviously. Will it move? 0.4 times 80. 32? 32. So it's 40 minus 32, then yes, it will move. 40 times cosine, that's what I said. It's 40, yeah, it's 40 times cosine 30 degrees. I'm sorry guys, I'm sorry. Confused me again. It's tension is 40 times cosine 30 degrees. That's correct. That's 34. Yeah. Minus 32. Will it move? Yes. Since it came positive, then yes, it will move. And it's 80 newtons as you got. The box will move. F T cosine theta minus frictional force equal to more than 0. And if we look at the calculation, guys, sit down. Let me finish this. Then yes, it's gonna, one of them is 34 as you said, the other one is 32, and yes, the box is gonna move. Guys, this is the end of chapter 5. You find in the slide, before I finish, you will find on the slide more examples. One of them two of them, they are related to